Here's a problem on the photoelectric effect. In this problem, we are going to calculate the photoelectric current ejected from a metal surface as a result of some light hitting the surface. So here's my metal surface in blue, right? It's what I've shown in blue. And it has an area of 1.8 times 10 to the negative 6 meters squared. I've just made this number up. I guess no, I didn't make the number up. This number already existed. I'm just using this pre-existing number in my problem. Okay, so there's the area. We know the frequency of our light. That's what's shown in red here. The frequency is 9.5 times 10 to the 14, and that's measured in units of hertz, which is just 1 over a second. And we also know the intensity of the light when it strikes the surface. It's 3.4 times 10 to the negative 3 watts per meter. And just as a friendly reminder, we're going to use this later, a watt is a joule per second. Okay? Now, we are also told one other thing. We are told, this is a very important fact, we're told that all of the photons striking the surface are absorbed. And that means that for every one photon, there is one electron ejected. Right? So for this photon, we have an electron ejected, and for this photon, we have an electron ejected. So for every one red squiggly line, an electron gets popped off and flying away from the surface. Okay, but I'm only going to show a couple so that my picture doesn't get too messy. So here, from this, we know that the number of photons reaching the surface per second equals the number of electrons reaching the surface per second. Okay? And the number of electrons per second is really, it's almost the charge. I mean, if I have 12 electrons ejected per second, that is charge, except that charge is expressed in coulombs per second. So I can take this E, and I can use the fact that one elementary charge is this many coulombs. I can just replace the E with 1.6 E negative 19. Because those two things are equal, they are replaceable. And now what I have, upon replacing in that way, upon substituting in, I have coulombs per second, or amps. That's my my current. So if I can find the number of electrons per second, I simply multiply, right? If it's 12 per second, I simply multiply that by 1.6 E negative 19, and we have our answer, our number of amps, our current. Okay, lots of things here. I'm going to erase this. This is a video, so I can erase whatever I want, and everything is still preserved earlier in the video. That's nice. And now what we have to do, the real challenge, is to find the number of photons ejected per second. And here's how we do that. We know that the total energy reaching the screen per second is equal to the number of photons times the energy of one photon per second. No, let's make it a little easier. I'm going to use my per seconds. Here's an easy way to handle the per second. You just write it up top. So per second, in 1 second, the total energy from the light is equal to the number of photons in the light times the energy of a single photon. And of course, we can take E photon and replace it with what it's equal to, h times the frequency of the light, like that. And that's very, very useful because the total energy is something we know. Per second, we know how much total energy is being emitted. Here's how we find it. Power divided by area is intensity. So if we take this and we multiply both sides times the area times A, now the areas cancel on the left, and the power is just intensity times area. So let's calculate the power. The intensity is 3.4 E negative 3 going to show my units here. Intensity is in watts per meter squared. The area is 1.8 e negative 6 meters squared. The meters squared, they cancel, leaving us with watts as our unit. And the power that we calculate is 6.12 times 10 to the negative 9 watts. Oops, 6.12 times 10 to the negative watts. But here I am, I'm going to use my trick. A watt is a joule per second. So in 1 second, or per second, the total energy getting sent from our bulb to the surface is 6.12 times 10 to the negative 9 joules, right? That's what this says. It's a ratio per second for each second. Per means divided by. Per second, this is the corresponding energy that is released from the light bulb toward the metal surface. And that is so nice to know, because I can take this value, 6.12, and I can replace it. I can replace E total with it. E total. That's what we just found. So per second, what we have is 6.12 e negative 9 joules. Now H is Planck's constant. And I'm out of room, so I'm going to erase some of this other stuff I've already done. But not forever, you just have to scroll back in time on the video to find it. And I need to multiply by one final thing, the frequency, which was 9.5 times 10 to the 14. And of course, a hertz is 1 over a second. So the second here cancels with this 1 over a second. They become 1. The joules on the right cancels with the joules on the left. And we calculate as our number of photons. What do we get? Let's see. We calculate. Comes to 9.7 times 10 to the 9 photons. So in each second, right, that's how much energy, we plugged in the energy released per second. So the number of photons released per second is exactly this, 9.7 times 10 to the negative 9 per second. And now, because we know that this is equal to the number of electrons released per second, right, because that's true, we can simply rewrite, if we care to, and why I do care to, the number of electrons released per second is 9.7 times 10 to the 9 e per second. Okay, I've added an e. Which means if I want to find the charge, it's this, and then I multiply, right? So the current is the 9.7 times 10 to the 9 Coulomb, E per second, and each E is 1.6 times 10 to the negative 19 coulombs. So the E will cancel, and what I'm given at the end is coulombs per second, that's amps, and this calculates to about 1.55 or 1.6 times 10 to the negative 9 amps. That's how much current we get flowing off of the surface if every single photon is absorbed by a corresponding electron. And that's how you solve these problems.